Hello, am I audible? So I welcome you to the live session number 2 of this particular NPTEL course, Technologies for Clean and Renewable Energy Production. I am Devarun Banerjee. I'm an PhD scholar and a Prime Minister's Research Fellow from IIT Delhi. So I'll start by just giving an overview of the lectures of this particular week, which means the week 2. The first lecture of this week 2 contains the basics of the pre-treatment, different pre-treatment techniques of coal, which includes uh, desulfurization and demineralization of coal. Furthermore, the different processes and its modifications in these particular processes, such as uh, let's just go to the particular lecture. Yeah, so the particular modification in the processes, such as in the fluidized bed reactor, how fluidized bed reactor basically is basically beneficial rather than a fixed bed reactor due to its greater contact between the coal particles and air. Therefore, the efficiency is more in a fluidized bed reactor. Furthermore, some metal oxides actually we can actually incorporate inside this fluidized bed reactor for in situ sulfur capture, which ultimately can reduce the pollution level because the outlet gas will not contain any sulfur then at that case. Further, the conversion of the coal in this particular process would be high, and the recycling of this particular unburned coal is much easier in terms of the fluidized bed reactor compared to the fixed bed reactor, which means that the conversion would be much higher. And there's different type of modifications in fluidized bed, like this JEA large scale fluidized bed combustion demonstration project is shown here. And the different factors such as the fluid bed size, yeah, and the mixing, the boiler size designs, those have very much effects on it. So after the fluidized bed reactor, the supercritical boiler, flue gas cleanup, all this have been discussed. As the boiler has been basically, it can be used in different phases, like subcritical phase, supercritical phase, extremely high supercritical phase also. Accordingly, with the when we reach towards this particular critical point, if we stay below the critical point or the greater the critical point, then what happens is that the heat rate and the efficiency which actually gets varied, which means that this the difference in this particular nature of the boiler, it actually affects, it can affect the efficiency also. right? So you can see here in this particular slide also that the subcritical has a 35% efficiency, supercritical has 37, advanced supercritical 42, and ultra supercritical has 44%. Furthermore, the oxyfuel combustion and chemical looping combustion are few other modified techniques to increase the particular overall efficiency and to reach to take the particular process, the overall process to an yeah, to an industrial level. The chemical looping combustion incorporates a metal phase which gradually then oxidizes and reduced from a between a metal oxide phase and a metallic phase. Furthermore, the gasification and direct liquefaction are two very important techniques which attempt to produce the fuel gases and further conversion towards the high value chemicals and basically majorly power and fuels. The second lecture contained the definition and basic chemistry of gasification, which means that the basic chemistry of coal gasification basically involves several number of reactions such as gasification and combustion with oxygen, which produces CO and CO2. The gasification with carbon dioxide, which means that the Boudard reaction, where the carbon in coal reacts with the produced carbon dioxide from the combustion and then further produces the carbon monoxide, which is a very important constituent of the syngas. Further, if the steam is also incorporated as a feed, then the gasification of steam actually can produce the mixture of carbon monoxide and the hydrogen. Also, this generated hydrogen, if it can be recycled back or in situ some reaction, if it happens, then the carbon and the hydrogen, it can also form the methane, which is a part of the natural gas. Further, the produced carbon monoxide can undergo water gas shift reaction with the inlet steam and produce carbon dioxide and hydrogen. And another thing is that uh, these reactions is there the mixture of the exothermic and endothermic reactions, which means is the gasification with hydrogen, water gas shift, and methanation reactions. Also, the combustion reaction are highly exothermic reaction, which means that it would generate some heat, and this generated heat would then be utilized in the gasification with carbon dioxide, such as the Boudard reaction, which is the endothermic reaction. This incorporates the basic chemistry of this particular coal gasification. Apart from that, the gasification reaction schemes and different steps are also discussed here. Different factors influencing gasification, and this production efficiency of this particular gasifiers, which ultimately produces a syngas as the major product. Those are also very important, and some direct advantages of gasification as an energy generation uh, process is also discussed in this particular lecture. A typical process flow sheet and utilization schemes of for gasification products are also overviewed in this particular lecture, which is also followed by the different types of gasifiers, advanced gasification, and some coal-based gasifiers. So, if you see here, the basic gasification reaction scheme involves some initial heating of the feedstock, which converts the particular feedstock, such as coal or whatever hydrocarbon is there, to a char and some volatiles. Then, separately, these volatiles and char both are gasified and ultimately produces a syngas. So if you see the chemistry here, because the volatiles, for the volatiles gasification, the the gasification occurs via an via the feed of the oxygen. This is a reaction is CnHm plus half NO2, which produces half MH2 plus NCO. On the other hand, the char gasification involves a steam as a feed, and which ultimately generates the hydrogen and carbon monoxide as a product. Furthermore, the different steps which are involved in this gasification process are drying, devolatilization, reduction, oxidation, and ash cooling. So when the feed is put from the top, and the oxygen or steam is given from the bottom, so the maximum temperature would be at the lower, the maximum temperature would be at the lower portion. So the oxidation would be at the lower portion, and gradually there will be some reduction due to less oxygen, and then with the further absence of oxygen, some pyrolysis would be there, and ultimately due to very less temperature, about 100 degrees Celsius, some only the drying would occur there. Ultimately we'll be getting some the syngas as an outlet. So these are the basically the overview, the different steps of the gasification process. And apart from that, different gasifier types, such as some fixed bed gasifier, fluidized bed, entrained bed gasifier, these are also discussed in this particular lecture. And some advanced gasification, and some list of some coal based gasifiers through the world, across the world, which are the different gasifiers available in a commercial scale. They are also discussed. The lecture 3 contains basically the second portion of the gasification part, which which basically consists of the outlet gas, which is basically syngas, how it is purified, the conditioning of the syngas, and the cleaning up of the syngas, how the syngas is actually utilized, and further how can we recover the heat which is constituted in that particular syngas, and then utilize that particular heat in a boiler to produce steam, and then again recycle back that steam to the gasifier inlet. In that way, that particular heat recovery things are also discussed. Apart from them, very important, the water gas shift reaction, because the large quantity of carbon monoxide is actually produced in the as a part of the syngas in this particular gasification reaction. This carbon monoxide is it can undergo a water gas shift reaction, so that we can produce a CO2 and H2 mixture when there is a steam available in the inlet. Apart from that, the particulates removal techniques are also discussed, and also syngas utilization is also discussed, about also the integrated combined cycle. Finally, apart from the gasification technique, some direct liquefaction process of coal is also interestingly is being discussed in the lecture 4. It's a very interesting topic also. Like basically the indirect liquefaction involves first the coal is converted to syngas, then the syngas is then converted to some the liquid fuels, the hydrocarbon fuels, and those will be further upgraded to maybe aviation fuel or other transportation fuel, high value, uh, high octane rating fuels. However, if we can carry out this entire process in a single way, in a direct way. So that would be very good. So in this manner, the different direct liquefaction process, such as whether it is single stage or two stage. In the single stage, solvent refiled cold liquefaction, Exxon donor solvent process, the H coal process, and the two stage, the integrated two stage direct liquefaction process, catalytic multi stage liquefaction. All these are discussed. So if we see the ninth lecture here. So basically the direct liquefaction process involves majorly a hydrogenation reaction where the high pressure of hydrogen with or without catalyst is required to convert this particular coal feed into a coal liquid, which is often higher calorific value than the feed coal. The lignite and lignite coal, subbituminous coal or bituminous coal, these are all there as a feed, and then for the further coal liquid is can be distilled as a gas oil, gasoline and kerosene production. The high temperature of about 400 degrees Celsius and a high pressure, but 100 to 200 atm pressure with hydrogen is very much important in this particular direct liquefaction process. The different types are already mentioned there. Solvent refined coal liquefaction involves a gasifier, basically as an intermediate step, which can supply the hydrogen required in this particular process. The excess hydrogen would be made up, would be supplied via the recycle stream, and then coal the coal slurry. The coal slurry is preheated to a very high temperature, and then it is dissolved under a high pressure, and then the vapor liquid separator separates the gas and liquid, and further washing and separation, it ultimately uh, results in the formation of the different different stages of the different distillates. Similarly, an Exxon donor solvent process is there. It's an carried out at a higher pressure than the earlier one, which is the solvent refiled cold liquefaction. However, it doesn't involve a kind of a gasifier to supply the hydrogen. Either the recycled hydrogen is supplied, or fresh hydrogen is supplied in this particular state. So that is the majorly the difference between these two states. So these are evolved via different companies, like Exxon donor solvent processes is evolved via this Exxon Mobil companies, or this solvent refined as evolved by some other companies. So thereby this kind of this commercial processes. Similarly, the H-coal process, which is actually the catalytic process, rather than about very high pressure, is about 200 atm pressure, and more than 425 degrees Celsius is important. And nickel molybdenum or cobalt molybdenum over alumina catalyst is important for this particular reaction. And the tabulated bed reactor system offers the substantial advantages over the fixed bed reactors. The reactor contents are well mixed, and temperature monitoring and control are more easily affected. So apart from that, some are the multi-stage liquefaction process, such as the catalytic multi-stage liquefaction or integrated two-stage layer liquefaction process. These are also discussed in this particular lecture number 4. Apart from that, the direct liquefaction benefits are also discussed along with the direct liquefaction challenges. So I'd like to know if there is any queries about this all these 4 lectures. Please do let me know. So if there is no query, we'll start with some sample problems. So you have to identify the operations which is happening at the P stage and the Q stage. This is basically a coal gasification technique. So we have to tell that whether it's a gas turbine, steam turbine, there is a or there is a opposite to that, steam turbine, gas turbine, but there is a pump and compressor where it is a pump and generator. So if you see that this particular is a coal gasification technique where after the gasification the raw syngas passes through some syngas cleanup and stages to clean the residues and to remove the sulfurs, and then further the syngas is passed through a process so that the hydrogen separator and ultimately the fuel cell to generate the electric power. Furthermore, the first step which is happening here is the generation of electric power after the syngas is passed through the process to produce the liquid fuels or chemicals, right? So this is the accepted. Yeah. So the first step is obviously the gas turbine, which would be providing us the electric power, and furthermore, the waste heat boiler takes up the additional energy which is there in the particular gas turbine process, and then the flue gas is. So the gas turbine is producing the electric power, and the waste heat is actually utilized to produce steam, which is then again recycled back to the gasifier, and then we are getting the flue gas, and additional uh, the additional heat we are which the energy source which are getting, it's again utilized to get the rest electric power, which is basically happening via the steam turbine. So the next question is that which of the following is a physical method used for removing the sulfur from coal? Oxy-desulfurization, hydrocycloning, hydrodesulfurization, or it's a caustic treatment. So the correct answer is the hydrocycloning, because actually all of these four are the removal method of sulfur from coal. However, the hydrocycloning is the only physical method here. The rest of the three are the chemical methods. So sulfur can be actually removed by these different physical, chemical, Biological methods. Among the physical methods, there is jigging, tabling, dense media processing, hydrocycloning, air classification. On the other hand, in the chemical processes, it's the oxydesulfurization, hydrodesulfurization, and also the caustic treatment is also there. So, in the oxydesulfurization, we employ the oxygen or air at an elevated temperature and pressure. The hydrodesulfurization, similarly, at an elevated temperature and pressure, we employ the hydrogen. And caustic treatment means the caustic soda or caustic potash is employed to remove the sulfur. Apart from that, some biological desulfurization is also an important technique, such as it uses some bacterial cultures, that's either a thermophilic or mesophilic bacteria, to oxidize basically the pyrite, which is the FeS2, and then uh, when it gets oxidized, then the sulfur would be actually removed from the coal sample. So there is a numerical problem. A low-grade coal is combusted in a fixed bed reactor. The composition of flue gas on a dry basis emitting from it is as follows. It's 15% CO2, 5% oxygen, and the rest is nitrogen. You have to calculate the percentage of carbon and hydrogen in the dry coal from this data. There are four options given here. Carbon is 95.98%, hydrogen is 5.21%, carbon 97.26%, hydrogen 2.73%, carbon is 78.92%, hydrogen is 21.08%, or carbon is 44.46%, hydrogen is 55.54%. So the correct answer is the 97.26% carbon and 2.73% nitrogen. The solution I have added here is the 15% carbon dioxide and 5% oxygen is mentioned as the flue gas. So I can assume that the rest is the obviously the rest is nitrogen. It means that the 80% is nitrogen. If we can assume that 100 mole of dry flue gas is the basis, then the 80 mole of nitrogen is there available in the flue gas, right? So nitrogen is inert. So we have to take that the entire 80 mole of nitrogen has come from the supplied air. So the 80 mole of nitrogen was there in also the supplied air. Yes, so if you consider that the air contains about 79% nitrogen and 21% oxygen, then we are getting that the supplied air was about 101.266 moles. Among it, 21% is oxygen. So 101.266 into 21 percentage, which means 21.266 percentage to 21.266 moles is the oxygen supplied. The rest of this, the 5 moles is in the outlet. It means that the rest of the 16.266 moles of oxygen was consumed. if we consider the combustion reaction as the C plus O2 CO2 and 2H2 plus O2 is the 2H2O, then considering the complete combustion, the 15 moles of carbon would be present in the dry coal, right? So because the 15 mole of CO2 we are getting as the outlet, so 1:1 ratio, 15 mole of carbon was there. It means that the 15 mole of oxygen was consumed in this particular reaction. The rest of the 1.266 moles of oxygen was consumed in the other reaction, which means that the hydrogen present would be the by stoichiometry would be the double of this 1.266 into 2, which means that 2.532 moles of the hydrogen was there. Now if we convert these moles into their respective weights by their molecular weight, means that the carbon was 15 moles, so 15 into 12 it will be 180 gram, hydrogen 2.532 into 2 is the molecular weight, so 5.064 is the hydrogen weight in the dry core. So the percentage of carbon is 180 divided by total of these two into 100%, and hydrogen is 5.064 divided by 180 plus 5.064. This is the percentage of carbon and hydrogen in this particular dry coal. The next question is that the favorable conditions for H coal process is 425 to 450 degrees Celsius under 200 atmosphere, 325 to 355 degrees Celsius under 200 atmosphere pressure, same temperature under 100 atmosphere pressure, or 425 to 455 degrees Celsius under 100 atm pressure. So the H coal process actually operates at the temperature of 425 to 455 degrees Celsius under pressure of 200 atmosphere, which is basically a catalytic process where a hydrotreating catalyst such as nickel molybdenum or cobalt molybdenum over alumina is used, and under an ebullated feed hydrocracker system. As with other processes, the yields are dependent on the coal. More than 95% overall conversion can be obtained with suitable coals, or the liquid yields up to 50% on a dry basis. The ebullated bed reactor system offers substantial advantages over fixed bed reactors. The reactor contents are well mixed and temperature monitoring and control are more easily affected. Which means that the basic difference between this fixed bed and the fluidized bed reactor with the ebullated bed reactor system, which is that the more the contact between this catalyst, the feed, and the overall like the hydrogen, is also a reactant, is much greater, because it's kind of a bubbling happens in the ebullated bed reactor, which doesn't happen in the fixed bed reactor. To some extent it happens in the fluidized bed reactor, but the ebullated bed reactor there is a recycle stream inside towards the reactor, and into that the hydrogen flow is uh, given. That is why the overall mixing and the overall heat transfer and mass transfer is very better, which means that if you ultimately you can compare the mass transfer coefficient, the heat transfer coefficient, that would be much greater than compared to the conventional fixed bed reactor. Ultimately involves a greater conversion and greater efficiency of this particular type of set of reactors. The next question is that if oxygen is replaced with air in gasification process, the produced gas is known as syngas, coke oven gas, gobar gas, or producer gas. Generally, the feed in a gasification process is air or steam or both also. But because uh, the syngas is the product, conventional product of a gasification process. On the contrary, if you want to replace the oxygen with air, what will happen? Because the conventional thing is the oxygen and the steam. So if we give air at the inlet, then what will happen is the nitrogen content will also be there. Is about 79% nitrogen is there in the air. So in the outlet gas, which is known as producer gas, which majorly contains nitrogen, is more or less inert. So about that kind of the content of the nitrogen which was given as a part of inlet feed will also be there as the outlet, and it will be known as the producer gas. And ultimately what will happen is that the percentage constituents of the hydrogen of the CO, CO2, methane, which uh, which actually consists or contributes to the high heating value of the syngas, which is typically about between 9 and 15 megajoule per meter cube of gas, will ultimately decrease because they're giving some inert gas as a high consistency. So the heating value would be decreased to about 4.5 to 6 megajoule per meter cube, and it will be known as the producer gas. Another numerical problem is that calculate the amount of work done in burning of carbon in a nickel-based CLC when the change in entropy delta is not is 420 joule per Kelvin and working temperature is 400 Kelvin, where it's given that nickel as a solid plus half O2 the gas, it gives nickel oxide as solid. Uh, there is a exothermic heat delta H is given as minus 396 kilojoule, and the carbon as solid plus 2 nickel oxide as solid gives CO2 as gas and 2 nickel metallic as solid. The delta H is given as 136 kilojoule. This one also figure is also provided here as for your reference. This is the example problem of chemical looping systems. The probable answers are 105 kilojoule, 153 kilojoule, 125 kilojoule, or 92 kilojoule. The correct answer is 92 kilojoule, because if you see this particular picture, there is the two simultaneous processes happening. One is exothermic reaction, one is endothermic reaction. What happens is that the metal uh, reacts with the air as an is an exothermic reaction. It gets converted to a metal oxide. It produces a large amount of heat because it's exothermic, which is given in this particular reaction. The nickel as a example, nickel when it reacts with the oxygen constituent of the air, it produces nickel oxide, and which is a highly exothermic reaction, produces 396 kilojoule of the kilojoule of heat per mole of nickel oxide production. This heat would then gets transferred into an simultaneous reactor, which is where this metal oxide is actually also gets transferred. It's separated from the nitrogen constituents in this particular system because we have given air as a feed. Then this nickel oxide gets reacted with the carbon, like with the fuel. The major constituents of the fuel is the carbon. Then it forms the CO2, and then it again gets converted or reduced to nickel, metallic nickel, which is an overall an endothermic reaction. So the heat generated from this first reaction is utilized in the second reaction, and then again this particular metal nickel metal is transferred into this particular exothermic reaction system when it again. So it's a kind of a loop. That's why it's termed as a chemical looping system. So how to solve this problem? We have this particular system here where this Q hot, which is the exothermic heat, is actually distributed into three parts. Whereas one is the Q naught, one is the Q cold, which is the utilization of this particular endothermic reaction. Q naught is the associated with the change in entropy and the work done. So Q hot is the delta H exothermic, which is 396 kilojoule. The Q cold is the inlet heat of this particular endothermic reaction, which is 136 kilojoule, and Q naught is the T delta S naught, which means that the T is given as a 400 Kelvin and delta S naught is given as 420 joule per Kelvin, which means about 168,000 joule, which means 168 kilojoule. So the work done will be the rest of it, because ultimately energy conservation would be there. So Q hot minus Q cold minus Q naught would be the work done. So 396 minus 136 minus 168 kilojoule would be the answer of the work done, the amount of work done in this burning of carbon, which is the 92 kilojoule. The next question is that which is the correct statement, which is rather this is not the correct statement about the advantages of gasification. Reduced carbon dioxide emissions, accurate combustion control, high thermal efficiency, or none of the above. So actually you can see that the whatever options have been given here are all actually are the advantages of gasification, which is the reduced carbon dioxide emission, accurate combustion control, high thermal efficiency, and also a compact equipment requirement with a relatively small energy footprint or carbon footprint also, because of this reduced carbon dioxide emissions. So the correct answer would be none of the above. The shift conversion reaction taking place during water gas manufacturing is given by what is the particular shift conversion reaction. It is carbon plus 2H2O is CO2 plus 2H2, carbon plus H2O giving CO plus H2, carbon monoxide plus H2O giving CO2 plus H2, or 2 carbon monoxide giving C plus CO2. So the correct answer would be the water gas shift reaction, which is the CO plus H2 giving CO2 plus H2, right? So the water gas shift reaction is actually very important for the syngas conditioning, because CO is generally produced as a constituent reaction, and as a part of the syngas, right? So the CO plus H2O, the CO plus H2 giving H2 plus CO2 is the water gas shift reaction, which is basically also based on the operating temperature. It can be further divided as two types: high temperature shift reaction and low temperature shift reaction. The high temperature shift reaction happens about at 320 to 450 degrees Celsius, and the iron chromium based catalyst is used. On the comparatively less footprint, less costly catalyst is used as a low temperature shift reaction 200 to 250 degrees Celsius, copper zinc oxide alumina. So copper zinc oxide alumina has a relatively higher selectivity uh, rather than the iron chromium. However, chromium has a high footprint, is usually a toxic in nature. That is why it is uh, also one of the disadvantages of this particular thing at the high temperature. However, it gives a very high resistance to sulfide and chloride impurities. As you know that the coal, whatever coal we are carrying in, it is not always the sulfur free or chlorine, this kind of impurities free, especially in India also. So uh, is very important. So like to gain a the resist to gain a high activity or high stability of the catalyst is important to act as a higher temperature with iron chromium catalyst. However, it is a um, very much not a very cost friendly attitude, because at the two different shift temperature shift reaction is in two different types of catalyst. On the other hand, which can, the cobalt molybdenum over alumina, this is the one kind of catalyst which can be actually used instead of using two separate catalysts in the two different low temperature high temperature shift reactor. This particular cobalt molybdenum over alumina can be used over a wide range of temperature, which can cover both the low temperature and the high temperature shift reaction. Also, based on the position of the water gas shift reaction in the overall flow sheet, if it takes place before the acid gas removal, it is called a sweet shift reaction. On the if it takes place before the uh, acid gas reaction, is called a sour shift reaction. And the positioning of this particular thing can actually influence the economy and also overall the product quality and the efficiency. The next question is that which is not the benefit of direct liquefaction of coal? High octane number, higher efficiency, low sulfur gasoline, or high capital cost? The direct liquefaction benefits actually involves higher efficiency than the indirect liquefaction technology. It actually generates a high quality of distillates which which have a higher octane number and also a low impurity such as low sulfur. It means that the quality of the distillate we are having is greater, which will be uh, beneficial for further upgradation to make the acceptable diesel blending stock. Also, uh, it can have actually a better carbon footprint than the indirect liquefaction technologies, and the development of direct liquefaction technology could lead to hybrid processes producing high quality gasoline and diesel, right? Which means that the high capital cost is not actually the benefit, because direct liquefaction of coal uh, due to happening at a very high temperature and pressure, about more than 200, like 200 atm pressure, more than 425 degrees Celsius, the capital cost, the quality of the reactor which would be requiring would be much greater, right? So the infrastructure cost or the capital cost will be very, very high. So it is not one of the benefit of the direct liquefaction of coal. Another simple problem is that in a fixed bed gasifier, air flow rate and feed flow rate are 25 normal meter cube per second and 12 kg per second respectively. The feed material doesn't contain any sulfur, nitrogen or chloride. The syngas contains carbon monoxide, carbon dioxide H2, CH4, methane, acetylene C2H2 2% and calculate the rate of production of syngas in normal meter cube per kg of feedstock. The correct answer is the 7.84 normal meter cube per the rate of production of the normal meter cube per kg of feedstock, the rate of production of the syngas. So how we are getting it is the so it's basically happening via the nitrogen balance. So whatever nitrogen we are getting in the feed via versus the whatever nitrogen we are getting as a product. So given as a certain air flow rate is 25 normal meter cube per second. So among it about 79% is the nitrogen. So we have given this amount of nitrogen and the same quantity of nitrogen should be there in the product. So the product contains CO, CO2, H2, CH4 and C2H2. So if we subtract it, so 100 minus this combined of these all these things, this is the nitrogen and there is 12 kg per second of the feed flow rate. So if we multiply this thing with the 12 kg per second, we will be getting this particular value and this putting in this particular formula, then we are getting this 7.84 normal meter cube per kg of the syngas production rate. The particular formula is this air flow rate normal meter cube per second into 0.79 divided by 1 minus CO plus CO2 H2 CH4 plus C2H2 divided by 100 and is multiplied by the feed flow rate kg per second, which is the 12. If we put these values, it will 25 is the air flow rate into 0.79 nitrogen content divided by 1 minus 45 plus 2 plus 25 plus 5 plus 2 divided by 100 into 12 kg per second is the feed flow rate. 19.75 divided by 0.21 into 12 is the normal meter cube per kg equals to the 7.84 normal meter cube per kg. The next question is that which of these forms of sulfur is present in coal? FeS2 organic sulfur, or the sphalerite, ZNS, galena, lead, PBS, or marcasite, or all of this. So the correct answer is that all of this, because if you see the sulfur in the presence of sulfur is actually in the form of the pyrite, the FeS2 or organic sulfur. This is the basically the major constituents, FeS2 and organic sulfur. Apart from that, the sphalerite, galena, marcasite, all these kind of things are also present. However, these are minor quantities. So if we also see that marcasite and pyrite is actually having a similar uh, formula, which is the FeS2, but their crystal structure, the morphology, all of these different. That is why there are two different name also given. One is a pyrite and another is a marcasite. So all of these forms of sulfur can be present in coal. Next question is that why fluidized bed reactor gives relatively higher efficiency? It provides more contact between coal particles and an air. Recycling of unburnt coal is possible, which increases conversion. Or it's both A and B, or is none of this. Hello, hello. So it's the correct answer as already also discussed that fluidized bed actually provides more and more contact because the particles or the coal particles are actually distributed throughout the entire reactor instead of the fixed bed, which is there is a packed thing within a fixed length. So more and more contact between the coal particles and the air would be there when the air is passing through this particular reactor. So there is a enough contact or at least a more contact than the fixed bed because there are very small gap in between them. So the contact would not be there. Good. So the more contact between coal particles and air would be there. Also, the unburnt coal of recycling is very much feasible in particular fluidized bed reactor, which ultimately can increase the conversion. So via both of these particular things, fluidized bed reactor can give a relatively higher efficiency compared to the fixed bed reactor. So the accepted answer are both A and B. The net energy efficiency and HHV of ultra supercritical boiler are 42% and 8126 BTU per kilowatt hour, 44% and 7757 BTU per kilowatt hour, 37% and 9300 BTU per kilowatt hour, or none of this. The correct answer would be the 44%, which is basically the highest, the ultra supercritical. So when we increase this particular type of boiler operation towards a more and more pressure and temperature condition, so it ultimately increases the net energy efficiency. So ultra supercritical boiler have it operates around 393 atmospheric pressure, 760 degrees Celsius, and it gives a 44% net energy efficiency. And the particular uh, high rating value, it is the 7757 BTU per kilowatt hour. However, uh, it can see that it's not usually that the whatever energy efficiency we are getting is directly correlated with the higher heating value. It means that it is basically the product, whatever product we are getting, based on that how good quality product we are getting. So the best quality product is the subcritical thing. However, the energy efficiency is less, so there is kind of a trade-off between both of these things. The net energy efficiency, the higher rating value. When you try to increase the energy efficiency by going towards an elevation of temperature and pressure from subcritical to supercritical to advanced supercritical and then ultra supercritical, energy efficiency would be increased, but the high rating value would be decreased. This is trade-off. This balance is very important. Okay, so that you have to understand, and that is the one of the important things. So the correct answer is the 44% in net energy efficiency with 7757 BTU per kilowatt hour HHV for the ultra supercritical boiler. In chemical looping combustion, at what elevated temperature, I have to give this particular range, the metal reacts with the oxygen in the air in an exothermic reaction producing metal oxide. between 100 and 200, 200 and 300, 400 and 600, or 700 and 900. The correct answer, the correct range is between 700 and 900 degrees Celsius. Uh, Between this temperature, the metal reacts with the oxygen in the air. Uh, it's an exothermic reaction which produces the metal oxide. Then this metal oxide is separated from the nitrogen because nitrogen is also present in this particular air, which doesn't react, acts as an inert carrier. Then its particular metal oxide is then fed to this particular reactor, which is called, can be called as fuel reactor or the reducer reactor. Then is metal oxide along with this heat which was generated in this exothermic reaction. It reacts with the particular fuel at an elevated temperature around 900 degrees Celsius, which reduces the metal oxide to metal and oxidizes the fuel carbon to carbon dioxide, and fuel hydrogen to H2O. Then again the same thing, the metal is transported back to this particular air reactor. So it's a kind of a looping system, chemical looping system it's called. And therefore the range which will be correct is around 700 to 900 degrees Celsius. Syngas can be used for various applications including liquid fuels, diesel and gasolines produced through what process? Fischer-Tropsch synthesis, Raynaud process, both A and B, or none of these. The accepted answer would be Fischer-Tropsch synthesis, which is basically a multi-step synthesis. So first the coal is gasified to syngas, then syngas is further FT process, which will be try to produce the liquid fuels such as diesel and gasoline, which is nowadays the research is ongoing to convert the coal in a direct one step, which is this direct liquefaction step. So inside this particular direct liquefaction, one is with the section of the gasifier. It maybe might not be depending on the process. So direct liquefaction step would be directly converting the coal to the this particular hydrocarbon fuels, the liquid fuels. The syngas conversion efficiency of thermal power plant is between what and what percentage for a single cycle system, single cycle steam power plant? 10 and 20, 20 and 30, 30 and 40, or 40 and 50? Is the 30 and 40 percentage between them. The single cycle steam power plant thermal efficiency is there. That is why it's very less. That is why to increase the particular conversion efficiency of this particular type of power plant, the combined cycle power plant is used. That is why is all the next question about is the syngas conversion efficiency of a combined cycle gas turbine power plant may be 50%, 60%, 70 or 80%, which is automatically you can see that it is greater. The options are also starting from a greater value, the single cycle steam power plant. So what is it up to 50%, 60%, 70 or 80%? The correct answer is that up to 60% syngas conversion efficiency we can get in a combined cycle gas turbine CCGT power plant. Which catalyst is used in the CTSL process? Is silver, it's zeolite, vanadium oxide supported on silica, or nickel molybdenum on silica? Sorry, on alumina. So the correct answer is the nickel molybdenum on alumina. CTSL is particularly a two-stage process, a catalytic two-stage liquefaction process, where the first stage temperature would be around 400 degrees Celsius, with an elevated temperature in the second stage about 435 to 440 degrees Celsius. So the overall hydrogen consumption, it is better managed at the lower first stage temperature, where the gradual temperature is increased in the second stage. Pressure is kept around up to 200 bar, and the catalyst which is used usually is the nickel molybdenum over alumina. And the important thing is that again the ebullited bed reactor is used in the both stages. So with is a better version of a fluidized bed reactor. And ultimately, CTSL process produces liquid product yield with low heteroatom concentration and high hydrogen by carbon ratio. The product is very closer to petroleum. So we can see that this much of research even on the commercial stage also, we have advanced that we can get directly petroleum from the coal instead of going via this FT synthesis, gasification followed by FT synthesis and all this further upgradation. A low-grade coal is combusted in the fixed bed reactor is the last question of our session today. Uh, a low-grade coal is combusted in a fixed bed reactor. The composition of flue gas in a dry basis emitting from it is as follows. 15.3% CO2, 4.1% O2, the rest is nitrogen. From this data, I have to tell that calculate the percentage excess air used in this process is what? 23.67%, 11.08%, 33.54%, or 46.42%. What is it? So the correct answer is 23.67%, and this is how we can get it. If we take the 100 mole of dry flue gas as basis, we'll be getting in 15.3 mole of carbon dioxide and 4.1 mole of oxygen as a product. The rest is nitrogen, which means that the 100 minus summation of 15.3 and 4.1 mole is the 80.6 mole of nitrogen we'll be getting as a product in the product stream. So this 80.6 mole nitrogen is also supplied with the air. So this 80.6 will be the 79% of whatever air has been supplied, which is coming out as 102.025 moles of air is supplied. So the oxygen supplied will be the 21% of this particular air. If we assume that 79% will be nitrogen and the rest 21% is the oxygen in the air. So it's coming around 21.425 moles of oxygen is supplied. So the consumption of oxygen is 21.425 minus 4.1, which are getting as a product. So the consumption is 17.325. So the excess is this 4.1 out of the consumption, which is the 17.325. So 4.1 divided by 17.325 into 100, which is the 23.67 percentage. Is the correct answer. I'm giving 2 minutes to sum up all the problems, and if anybody has any questions, please ask, and to check this particular problem also. We'll also try to, there is no question, also try to discuss quickly the tutorial problems. Uh, the fixed weight gasifier, the air flow rate, feed flow rate are given as a 10 nanometer cube per second and 8 kg per second respectively. The feed material doesn't have any sulfur, nitrogen, and chloride. Syngas contains carbon monoxide, CO2 2%, H2 30%, and methane 5%. So the rate of production of syngas is, this kind of problem I have already solved. It should be proceeded via the nitrogen balance. The fuel gas production equals to the air flow rate in nanometer cube per second into 79%, because air generally has a 79% of nitrogen, divided by whatever nitrogen would be there in the particular outlet gas, right? So it's 100 minus summation of CO, CO2, H2, CH4, and C2H2. Apart from this particular hydrocarbons, the rest of the gases were assuming as the nitrogen into the feeding rate. So these values will be for the per mole per kg of the whatever coal has been burned. A peat sample has the following composition: carbon 37.5%, hydrogen 8.8%, oxygen 27.6%, nitrogen 0.4%, and sulfur 0.1%. Moisture 20.5%, ash 5.1%. So have to calculate the yield of hydrogen and CO, and also have to tell that the molecular formula and the heating value of this particular sample, and there is one relation is given, and both of this particular basis, on wet basis and dry ash-free basis, both of these basis you have to determine the molecular formula and heating value. So what has been done is that basis of 100 gram of this particular sample has been taken, and uh, the composition is provided, right? So dividing it by the respective molecular weights will give us the moles of the particular elements. The molecular formula of ash is given as 56. Moisture is will be taken as H2 molecular weight, water. So 18, and the rest of this are all known for us. And also there is certain oxygen from moisture. So in H2O is one mole of oxygen, which means that the 16 gram per mole of oxygen is there in the moisture, per mole of moisture, and 2 mole of hydrogen is there. So accordingly, if we put this all these values in moles, we can get easily the molecular formula, right? And the conversion from the wet basis to dry ash-free basis will be just the removal of this particular moisture and ash, and then compared it with the whatever present value we are having. 37.5 was already we are having 37.5%. 37.5 into 100 divided by 100 minus moisture and ash. So it will be around 50.54%. And whatever this kind of percentage we are getting, simply put these values in this correlation. We will be getting this higher heating value on dry and ash-free basis. And the gasification reaction, you have to assume that it would be like the molecular formula we have already determined, plus FH2O plus GO2 be giving HCO2, IH2, JCO, D by 2 N2, KSO2, MH2, and NH. So A, B, C, D, these values are we have already known. Now the important thing is that we have to have given us other things also, that mass of sample via mass of oxygen is 0.8, which means that the per unit per mole of sample when it was used, that the mass of oxygen, how many mass of oxygen was there. So if we can get it, like 99.8156 is the molecular weight of the sample, divided by zero point 0.8 would be given as the 3.899 moles of oxygen was actually utilized, which means that the G, which is the GO2, which is taking as a reactant, so G we are getting as 3.899. In a similar way, the mass of steam by mass of sample is zero point 0.1 is given. So there is certain F moles of H2 are we have assumed is which are as a reactant in this particular gasification process. So whatever steam has been used is this 0.1 into our molecular weight. So divided by 18, which is the H2 molecular weight, is 0.555 moles. So F also we are getting as 0.555, 0.555. Okay. So putting all these values in these correlations, we will be getting like 2I plus 2M is equals to 12.188, which means that I plus M would be uh, divided by 2 in the right hand side is 6.094 will be the equation A. In a similar way, uh, and also this thing was also given that J equals to 2I. J equals to 2I. This thing. Assume the carbon monoxide and H2 ratio in syngas is 2:1, right? So simple put, the 2I in place of J, one more variable is gone now. So converted this particular equation, H plus J equals to 3.125 is H plus 2I equals to 3.125. So and another equation what we are having is 2H plus J plus 2 into 0.0031 plus M equals to this particular values, 2.864 plus 0.555 plus 2 into 3.899, right? So here we are getting this particular three equations. I plus M equals to 6.9094, H plus 2I equals to 3.125, and 2H plus 2I plus M equals to 11.211. Three equations, three unknowns, you can solve now. So just some operations like C minus B you have to take, uh, then it will be giving us H plus M equals to 8.086. Again, the whatever equation this is we are having, name it certain like D, and then D minus A, if we do, the M would be cancelled out and we'll be getting an equation of between H and I. So H minus I will be 1.994. Again, we are already having one equation between H and I, which is B, equation B, H plus 2I equals 3.125, right? So just simply do this operation where 2E plus B, which means that H, uh, the I would be cancelled out, so 2H minus 2I plus H plus 2I, so I would be cancelled out and ultimately we'll be getting H as 2.37. Put this value of H in this particular equation, we'll be getting I, and put both of these values in this particular equation and we'll be also getting the value of M. Just put all these values and get the entire answer. And this particular kind of problem we already solved, the weight ratio, the percentage carbon and percentage excess air also. So that is all from my side. If anybody has any question, please ask. Otherwise, uh, we'll wrap up this session. Okay. So thank you all.